Hello. So I am David Meyer from MSC Software, and I am the business development manager of the product VIRES Virtual Test Drive for MEA. And today I will present you what do platforms that simulate autonomous driving realistically and reliably look like. But before that, I would like to start by explaining why do we need platforms to simulate autonomous driving shortly. And I will start this with a small cartoon. So as you can see on this cartoon, you can see an autonomous driving vehicle, and the passengers of this autonomous vehicle seem really afraid, at least one of them. And the passengers would like the vehicle to go slower, to be careful of the bicycle, to brake, to watch out the dog. By the way, I don't know where this dog is on the cartoon, but anyway, this is a cartoon, and it is actually what all drivers like you are confronted with every day while driving. So, and every day you probably encounter a different situation. So being aware of this complexity, you can easily imagine that it is impossible to validate an autonomous vehicle only with real tests. You have to definitely to leverage a simulation. So what do simulation platforms for autonomous driving look like? Well, you will first need to create the environment on which you want to test, of course. And how do you do this? It is like in real life, actually. You will start by some construction work. You will start by building the road network. Here you can see an highway environment, but you may need to create a junction, a curve, or a roundabout, actually any type of road geometries, any type of road networks that you want to reproduce from real life. Once you have created your road network, you will need to add some traffic rules on this road. It can be traffic signs, but it can be also some road markings or some specific lanes like bicycle lanes, bus lanes, any type of rules actually. And these rules depend on the country that you want to, on which you want to build your environment. So you have to have a really big database of traffic sign and lanes within your simulation tool to allow this. Then what do you do usually when you are ready with the road network and the rules? You will start building some buildings around the road. And this is not only for the simulation environment, this is not only to make the environment look nice. It is actually really important because the light will reflect differently depending on where you place different buildings. And you may also want to hide some objects behind some buildings, like pedestrians, for example. So it is really important to build such an infrastructure as well around your road. And for the same reasons, you will need also to add some landscape around the road. So it can be a landscape like the one you can see on the picture here, but you can actually design your own geometries and import whatever you want from an object. So these are the different static environment that you need to build, but you also need to add some dynamic content onto this environment. With what you will start usually, you will start by adding some vehicles around on the road, and these vehicles can have different types, or you will probably need to simulate some cars, some trucks, also some tractor-trailer combination, or motorbikes, excavators, any type of vehicles. So you need as well here a big database of vehicles to be able to simulate them. You don't need only vehicles, you need also some pedestrians on the road. So to make for some specific test. So we can see here some pedestrian, but these pedestrians should have some, they should move, they should have some gesture, so they could cross the road, or they could drink a coffee, they could also hanging a phone or drinking a coffee, whatever. You may also want these pedestrians to move on new mobility devices like here, because it's quite, so you can find it everywhere right now, and it's really important as well that your autonomous driving function works with this type of new mobility devices. There's one thing that I haven't mentioned here on the dynamic part, so you need to add one last thing on this dynamic environment. It is traffic signs that are dynamic. So, for example, the traffic lights that you want to have some color depending on the time or different events, but it can be also some traffic signs with some specific text or some speed sign that are changing depending on the time of day, etc. So we have seen here shortly what do we need in terms of static and dynamic environment. For this creation, you need a toolset as well as a really big database of content, which is country specific. So this is something that VTD can provide, but after the environment creation, you are not ready. You will need to animate your environment. What you need here is an accurate traffic model as well as a vehicle dynamic model. This vehicle dynamic model, which defines how your car moves, should be configurable depending on what you want to test. If you want to do some basic functional test, a bicycle model may be enough. If you want to do some accurate test like vibration, driving over a speed bump, then you will need a really accurate model. And you will maybe need as well a really accurate models like the ones that we can get from Adams that can be plugged to VTD. I will not go here in details about the animation part. We have a webinar coming soon on 21st of October, which will explain how to integrate this complex vehicle dynamics model to VTD. So you can register to this webinar for free on the MSC software website. So please don't hesitate to do so, and you will have more information about these topics there. For the animation part, I will just show you a video to show you how it could look like. And so you can see here on this video some pedestrians walking around. You can also see some Segway, for example, motorbikes, vehicles, so nature. Here it's like an highway environment, but you can also decide to design a city environment or a country road. Actually, anything you want to reproduce from real life. So we have seen that you need to create your environment and that you need to animate it. But what comes next, it's a perception part. So this is a third step in a simulation environment. And this is probably the most important part in the simulation environment, because this one will generate the input for your system and the test. And this is what you want to test, so it should be accurate. So how does this perception look like? Well, perceiving the environment depends on what you want to test. Do you want to test perception algorithm, or do you want to test control algorithm? With perception algorithm here on the left, what I mean is object detection and classification. Like, for example, a camera-based detection algorithm that will detect and classify correctly all the objects on an image. You may want to test this type of perception algorithm, for example. On the right, with control algorithm, I mean the decision making. Should the car brake? Should the car accelerate? should the car steer? Typically, all the ADAS and safety algorithm, as well as autonomous driving algorithm. Which type of perception you need for this? For perception algorithm, what you should get for a simulation environment is a physically based sensor, which will give you information on pixel level with color, distance of the objects that is encountered, the number of hits, etc. And to test your control algorithm, you will need an annotated object list as input of your system in the test. And this annotated object list can be object velocity, can be object type, occlusion plane, coordinates. This is a simplified sensor. Independently of what you want to perceive from the environment for your system and the test, you will want to inject some errors on the signals. I will come back to this noise later on in this presentation, and I will concentrate only on the physically based sensor, which is actually the most complex part. So the simplified sensors is much easier to implement. So I will concentrate on this part, and I will explain this physically based sensor with two examples. One camera and one lidar. I will start with the camera. So you can see here two different pictures that have been generated with VTD. The one on the left is generated with OpenGL, and the one on the right is generated with ray tracing. You can clearly see a difference in terms of reflection between these two pictures. The reflection with ray tracing on the right are realistic, whereas the one with OpenGL on the left, not, because they are rendered from the camera position and not from reflection position. But the image with OpenGL can be generated with a frequency much higher than the one with ray tracing. So here, for this example, with our definition of 1920 pixel times 1080, we are able to generate the OpenGL picture image in a frequency with 60 frames per second. Whereas for the same definition with ray tracing, we will provide you this image with a frequency of 0.5 frames per second. So you can clearly imagine that ray tracing costs time. We can provide you with both solutions. Our solution is really scalable, so you just need to take what you want depending on what you want to test. If you want to test in real time, then you should probably go with OpenGL. If you want an extremely realistic image, then you should go with ray tracing. Independently of the solution you choose, OpenGL or ray tracing, your camera should be configurable. And there are different ways of configuring the cameras. And I would like now to explain this part. And I will start with a pinhole camera. You can see here an example of a pinhole camera view, which has an aperture angle much lower than 180 degrees. And there are different ways of configuring this camera model. So either by, you have different options. You can configure either by configuring the OpenGL frustum, or configuring the intrasec and intrasec parameters, or entering directly the projection matrix. For the first case, OpenGL frustum, you will specify the near and far clipping planes, as well as a horizontal and vertical field of view. For intrasec parameters, you will enter the width, the height, the focal length, and the principal point of the camera. And for the projection matrix, you will directly enter the matrix values. Here it's an example of the pinhole camera, but you may want to generate an image with an aperture angle close to 180 degrees or above it. And for this purpose, a pinhole camera is not made for this. You will need a fisheye camera that produces visual distortion. Here it's an example of a fisheye camera. It sees a 180 degrees field of view in this example with equisolute mapping. And compared to the pinhole camera, you have a much wider field of view. So you can see here, for example, on this image that you can see more the landscape on the road. With our fisheye camera, we're able to obtain a 360-degree view of the scene, and with other mapping functions, that's the one I explained before, the equisolute mapping. And to configure the fisheye camera, you need a tool, of course, to do this, because you need to configure the lens mapping and distortion parameters. We have seen two different examples of the views that we can obtain. These were perfect images. As I said before, you may want to add some noise in the images so that you can test in a more realistic manner. So I will show you now an example of a noise. And in this example, it's noise on pixel level. And it is a statistical noise. So it means the noise is changing at every frame. I hope you can see clearly this effect on the video. This is an example. You can, of course, imagine other type of noise, like dirt on the lens. You can also imagine lens failure, like chromatic aberration. This chromatic aberration will generate a blurry image, like you can see here. And this chromatic aberration, you may want to configure it as well. So you need a way to configure it. And additionally to the noise or the lens failures that you will do, you may as well want to post-process the image with image patterns, because if you feed directly your camera with images, like on the hardware in the loop system, your camera will understand some specific image pattern. So it could be, for example, a YUV pattern that your camera would like as input. It could be as well RCC pattern, and it exists other type of patterns like Bayer patterns or tone mapping. We are able to provide you with this pattern. I will not go here in details anymore for all this type of patterns, and I would like to come with a lidar example now. So I hope you had a quite good overview of this camera possibilities here. Let's move to the lidar. In comparison to camera, the lidar usually use a much smaller definition in terms of pixel. You are not in a 4K pixel range, for example. So this allows us to use ray tracing for these sensors, for these physically based sensors, which is actually good for lidar, because for a lidar, you may want to take into account some several hits and reflections, and you can do only this. You can have this information only with this ray tracing technology. So if you're able to run in real time or not with this module depends definitely on the accuracy that you are researching, on the definition. So for example, here what we have we have two different lidars, the high resolution lidar and the low resolution lidar, but this is just example. We can be definitely in between as well. For the high resolution lidar, it's a definition of 1800 times 300 rays with 4 rays widening per pixel, and we are able to provide this image with a frequency of 5 frames per second. Whereas for the same definition, for 10 times less definition on the bottom here, we will provide you this data with a frequency of 25 frames per second. So again, for the LiDAR, the solution that you want should be really scalable and should really depend on what you want to test. So the simulation environment should be able to provide you exactly the input that you are searching for. Here you can see the configurable parameters of a LiDAR. So if you want to test a specific LiDAR, you may need to configure it as the real part. So you will want to configure the number of rays, and as well, of course, the field of view or the lookup table that you will configure for per pixel for the direction and intensity. So you can choose between the two options. You will also want to have the configure the maximum reflection depth. You may also want to define the type of attenuation that you want for the rays that you are sending. And a last feature that you want to configure probably is an offset around this ray, because let's imagine you have a ray which hits an object which is 100 meters away. For this object, you will not meet this object with a single point in real life. It will probably be a cone. So you may want to configure an offset around this ray by yourself in the simulation environment, so that when you hit an object which is far away, you will hit a cone, and the simulation environment will provide you with the information you want within this cone. It could be, for example, within this cone, the highest intensity. What you would like to configure as well for the LiDAR, it's probably the number of hits that you want to take into account. And additionally to the parameters of the LiDAR, you will also need a database of physically based buildings, or with this I mean all the building infrastructure that you add in your environment should have some information about the materials, because you can see here clearly on the example the window has a different material properties than the concrete, and the reflection is totally different. So you have definitely to take these material properties as well into account. So you need a big database of this type of infrastructure. As an output of your LiDAR, so you can have different outputs, but you will probably take the distance, the elevation, the azimuth of the hit. All these outputs of the simulation will go into your LiDAR, so that you can test the detection and classification of the object based on this information. So distance, elevation, azimuth. You can have also the rest intensity of each hit, the coordinates, and even more options like time of signal return if the object was static or dynamic, and any kind of other information. This was for the LiDAR, for the physically based LiDAR, like on the bottom of this picture. If you don't have physically based information, the reflection will not be really correct, as you can see on the top pictures here, with a basic LiDAR, which doesn't take into account these material properties. So you can definitely see a different in terms of reflection of the rays. So we have seen here some properties about the LiDAR model. We have seen before the camera model. You may want as well to map both information together, because it can be really interesting to map the LiDAR data onto the camera image for debug purposes, For example, if you want to see the field of view of the lidar, it's much easier to see it in an image. Or if you have a specific debug to do, you can directly see with a color code which object you have hit, and the color code can be different depending on the information you want. You could imagine having a color coding for the distance, or a color coding for the intensity of the rays, or coordinates, or actually whatever. You can configure the color coding as you want. And this is, I think, interesting for debug purposes. So with this video, I will end up my my presentation on the what do simulation platforms realistically and reliably should look like. It's time now for takeaways. First of all, of course, you may all know that simulation is definitely needed for the validation of autonomous driving systems. This simulation platform should allow you to easily create, animate, and perceive the desired environment. And for all these three steps, you need reliable and realistic models. But not only, your models need to be scalable as well, depending on what you want to test. Because of course, you are searching performance always. And for some use case, you will prefer to have simple models with extremely high performance, whereas for some other use cases, you will need accurate models with a configurable performance. What I didn't mention during this presentation as well is that independently of the environment that you are you want to test, you may need to test it on different platforms, so on the complete V-cycle from mill to hill, or to vehicle in the loop as well. And it is important that the simulation environment provide you with a good structure so that you can build your environment and animate it independently to the platform on which you are testing it. So you can, for example, imagining creating a test in sill and reproduce it in hill without to have to change anything in your environment, except of course the interface for your hill. This is really important as well to take into account for a simulation environment. And I will end up with two advices for this presentation. First, do not miss our VIRES Virtual Test Drive User Conference in Frankfurt from 25th to 27th of March 2020. And second advice, I've mentioned before, we have a webinar on the integration of Adam's vehicle dynamics model into VTD on 21st of October, so it's on Monday. You can register for free on our MSc website, mscsoftware.com, so please do not hesitate to do so. Now it's time for question. My colleague Daniel Wiesenhutter, who is responsible for VIRES VTD development, should be connected now to this presentation as well, and he will be happy to answer your question in details. Thank you.
Thank you, David, for your presentation. Yeah, I see that Daniel is also online. Hello, Daniel. Can you hear us?
Yes, I can hear you. Can you hear me?
Perfect. We hear you too, which is good. Regarding the questions, we already got some questions. I would just read them out for you both, so you can answer those. Well, let me start with the first question, which is, well, the term scalability has been coined a few times in the presentation. Now the question is, how scalable is VDT, or virtual test drive, exactly?
Yeah, VTD is consisting of multiple modules and components, and our approach is that these components are communicating over network to each other, and we have also a central component which is synchronizing everything, so it's possible to start processes and components on other machines, like other computers, and we have systems, for example, for simulators where we have one main computer for all the logic computation, and then we have, for example, up to 10 or 20 other computers which have like views on the simulation for a cave or something. And the same you can do also for sensors or everything else. So you can distribute the processes on multiple machines.
Thank you. I think following up on this is also a question about determinism. How deterministic is your simulation?
So we have determinism in our simulation, but that also always depends on the external model or the system under test, which is mainly part of the simulation. So that always depends if it's needed in the simulation run or not. But we have configurations where we are running deterministically, but in other cases there may be not deterministic modes with other components, or where it's just not needed, for example, for simulations with human interaction.
Thank you. Then there's the question, you presented like the trade-off between resolution and frame rate, and now somebody is asking if you would have to decide what's more relevant for the simulation, because yeah, kind of you have to make a decision if you want to focus on the one hand or the other side. So are there specific scenarios where you should, have a closer look at resolution or frame rate? What would you say?
Yeah, that's clearly up to the use case. So if you have a hardware in the loop system, or for example a camera in the loop system, the real time is the main issue, and you need to deliver images in the correct frame rate that an algorithm or a real hardware algorithm, which will be part of a vehicle, is getting the information in time. So if you have something like that, you need always focus on performance, and maybe will have less quality in the images in order to provide images for testing. If you have another example, if you have machine learning, for example, or some software in the loop system, where you may have where you just feed information which should be high quality, you can take more time for the creation or the rendering of the image or a sensor output in order to have a more quality image, and it doesn't affect the system because it's not having any feedback, because you have open loop, or you just save the images for machine learning and train later on. You're just creating data sets. So depending on your use case, you need always to find the best measurement. But these two examples are, I think, the two extremes you have. So hardware in the loop and open loop and software in the loop systems.
Makes sense. Another question has come in, for example, here, you presented different sensor technologies like lidar, radar, EDC. Are you able to simulate different sensor technologies in parallel?
Yes. So as mentioned before, we have components which are simulating one sensor output. For example, we have a component for rendering images. We have a component for rendering a lidar output, and you can distribute them on two different machines or on two GPUs. And in that case, they can be simulated and executed in parallel, and you can also get and receive the information in parallel.
And now I have one last question for the moment. That is in hardware in the loop, where camera directly looks at the image on screen, which pattern or patterns to be chosen in the camera model? For example, when it's about ray tracing and YUV pattern.
I think YUV pattern makes only sense if you feed that image directly to a camera. If you have like a monitor, so if you have a camera in the loop system where a real camera is tested and you have a real lens, you normally have a monitor which should produce a highly quality and realistic image. So the focus there is to get a realistic image with correct light levels to the monitor. The problem in the case where you have a monitor involved is that the monitor cannot visualize the light levels there might be in reality. In contrary, if you're having a direct feed to a camera, you can simulate like HDR images with higher bit rates, and you can transfer instead of 8 bits per channel or 12 bits per channel, you can transfer more higher bit levels, which can deliver information from light levels from reality. For example, looking into the sun, it's a very, very difficult use case to have it with a monitor involved.
All right, thank you. And in the meantime, I got one last question that came in. I'll just read it out. In the lidar visualization demo, it seems like they are capable of seeing also reflections. In reality, I understood that they are not able to see them. How big is the error therefore introduced?
Yes, let me just explain the images you have seen. So they were color coded as well. So the red channel was for the intensity at the first hit. The green channel was the intensity at the second hit, and the blue channel the remaining reflections. And we use ray tracing for our lidars, and so we can save the intensity at each reflection, echo, hit point, whatsoever. And it's normally a real lidar would have maybe only one response of intensity, which is the accumulated intensity of all 3 channels. But our software is also used for prototyping, and that's why we have also use cases where they want to simulate how much intensity is at some second or third reflection level. So that's the use case for that approach. But I think for the current real lidar systems, it's not very important. So far I'm knowing, but I'm not the best expert at lidar systems.